Welcome to The Explainer. Today we're going to decode one of the most elegant and powerful tools in all of science, the periodic table of elements.
But first, let's kick things off with a puzzle. Imagine your job was to create a filing system, not for boring office papers, but for every single fundamental ingredient of reality. You know, all the stuff that makes up you, me, the planet, the stars, everything. I mean, where would you even start?
For most of history, that's exactly what chemistry felt like. It was just this chaotic mess of disconnected facts. It was like a library where someone had just thrown all the books on the floor. Yeah, you had gold, you had oxygen, you had iron, but there was no order, no system connecting any of it.
And then, in 1869, this Russian scientist, Dmitry Mendeleev, had a huge breakthrough. He started sorting the elements they knew about, but not by something random like their color. He used their atomic mass. And as he laid them all out, something incredible started to happen. Elements with similar personalities kept showing up at regular, predictable intervals. A stunning pattern was emerging right out of the chaos.
But here's the thing that takes Mendeleev from just being a smart guy to being an absolute genius. It wasn't just what he put on his table, it was what he dared to leave out. His table had empty spaces in it.
I mean, can you imagine the confidence? These gaps were basically a dare to the entire scientific community. He was saying, hey, there are elements we haven't even found yet, and I'm telling you, when you find them, they're going to fit right here. And get this, he even predicted what they'd be like, their properties, with incredible accuracy years before anyone ever discovered them.
So Mendeleev's idea was brilliant, but it wasn't quite perfect. He was so close. He thought the key was atomic mass, but the true secret code, the real organizing principle that would unlock the whole thing, was something even more basic.
And that brings us to the modern law. And this is where it all just clicks into place. It turns out that all those repeating patterns make perfect sense when you arrange the elements not by their mass, but by their atomic number. And that's just a fancy way of saying the number of protons in an atom's core. That was the real key.
So why? What's so special about that one number? Well, it's because the number of protons dictates the number of electrons orbiting around that core. And it's those electrons, you see, that control, well, everything. An element's entire chemical personality is all about its electrons.
Now, these electrons don't just buzz around randomly like a swarm of bees. Nope, they live in very specific regions of space called orbitals. You can kind of think of it like a giant apartment building with different floors and different rooms. And just like any apartment building, there are some very strict rules about who gets to live where.
This whole electron real estate market is governed by just 3 simple rules. Rule number 1. Electrons are kind of lazy. They always take the easiest spot, the one with the lowest energy. They fill up the ground floor before they even think about moving upstairs. Rule 2. They need their personal space. No 2 electrons can be in the exact same state, so if they have to share a room, they'll at least have opposite spins. And finally, Rule 3. They really prefer not to have roommates. An electron will take its own empty orbital before it's forced to pair up with another one. And believe it or not, these 3 simple rules build the entire magnificent structure of the periodic table.
Once you understand those rules, the periodic table totally transforms. It stops being just a chart of elements and becomes more like a city map with really distinct neighborhoods or families. And just like in a real city, an element's address on this map tells you everything you need to know about its personality.
And this really gets to the heart of it, the behavior of 3 key chemical families. It all boils down to how many electrons they have on their outermost shell, what we call valence electrons. That one number basically decides their entire social life.
Okay, first up, the alkali metals over in group 1. These elements have just one single, lonely electron in their outer shell, and they are desperate to get rid of it so they can be stable. They're the generous givers of the table. This need to offload an electron makes them incredibly reactive. So reactive that elements like sodium and potassium will literally explode if you drop them in water. Then you swing all the way over to group 7 and you find the halogens. They are the complete opposite. With 7 outer electrons, they are just 1 electron away from having a perfect stable set. So they are intense takers. They will do just about anything to steal that one last electron, which makes them the most reactive nonmetals on the entire table. And finally, we have the cool kids, the aloof elite. The noble gases in group 0. These guys have a perfectly full outer shell of electrons. They've already reached chemical nirvana. They don't want to give electrons, they don't want to take them, they don't want to share them. They are stable, unreactive, and they'd really just prefer to be left alone. So you see, this whole organization isn't just about making things look neat and tidy. The table is a predictive map. Just by knowing an element's address,
its group and its period, we can predict how it's going to act without ever even having to see it.
Take the size of an atom, for instance. Now, as you go down a group, atoms get bigger. That makes sense, right? You're adding whole new electron shells, like adding new floors to that apartment building. But, and here's the weird part, as you go across a period from left to right, the atoms actually get smaller. How is that possible? Well, you're adding more protons to the nucleus, and that stronger positive charge pulls all the electrons in just a little bit tighter.
This predictable pattern also tells us how greedy an element is for electrons, a property we call electronegativity. And that greediness increases as you move up and to the right on the table. This makes fluorine, sitting right up there in the top right corner, the most electron-hungry, the absolute greediest element of them all.
And this is why this all matters. This beautiful, logical order is what allows us to understand and, well, to engineer the world around us. From designing life-saving medicines to creating the advanced materials in our phones and computers, it all comes back to the predictive power that was born from this one simple chart. Out of chaos, we found order. And from that order, we built all of modern science. So the next time you look at a periodic table, don't just see a bunch of boxes and letters. See it for what it truly is, a map of cosmic possibilities, a cheat sheet from matter itself. And maybe ask yourself, if this much elegant, predictable order could emerge from the chaos of the elements, what other hidden patterns are just waiting out there for us to discover?